people focus. My stage for everyone.
Hey, good morning, everyone.
Good morning, sir.
Hey, good
Neeraj sir
morning.
is here. Morning.
Hey, good morning, Raj.
Sir, just give us couple of minutes. We are doing some setting here.
Okay, yeah, take your time.
Sir. Hide participants without video. अच्छा, बस उसको hide कर. अब ये स्टेज सबके लिए है सिंक. कोई लेआउट से अच्छा यदि हाइड पार्टिसिपेंट विदाउट वीडियो पीपल फोकस ये हटाना चाहते हैं हटा दो. यहाँ पे जा एक जहाँ दिख रहा है उसे बता रहा हूँ. सेकंड जो स्ट्रीम हो रहा है उसमें सर का फोटो दिखेगा. सर स्ट्रीम उससे कुछ होता नहीं. आप ऐसे भी रख लेंगे कोई यहाँ पे कैसा स्टार्ट सर हो गया कर सकते हो. अभी जा रहा है ना स्ट्रीम हो रहा है ना. हेलो. हाँ you mean
Yes.
yeah we can start now.
Okay, very good.
I
Let me
सुना दिया ना.
chat ready.
Okay we made you the co-host too. Yeah.
Okay. All right. So let's start today's lecture. Good morning, everyone. So today is our day 3 lecture for our ND inverse problems and signal processing. Okay, so I believe we had a very productive day 1 and day 2, going over the fundamentals of ND inverse problems and signal processing. So today we'll continue to talk about the topics on data processing, particularly on feature extraction, probabilistic ND imaging, and monitoring. Okay, good. Again, stop me anytime if you have questions. I believe we had very good discussion yesterday, so let's continue doing that today. Okay, any questions before I start today's lecture? If no, let's continue. Well, so first of all, I think it will be good to talk about NDE sensing and differences between sensing and monitoring. Well, before talk about sensing and monitoring, let's find the subtle difference between sensing and data acquisition. Are they the same or not? Well, let me define those two terms here. Sensing is a way that quantifying is a quantifying measure proportional to a physical phenomenon. And in order to do sensing, you can develop different ways of doing sensing using sensors. Well, acquisition is a mean to convert and store the measure in digital form. So you can see the difference between sensing and acquisition here. Well, when I have some kind of source and I need to capture that in energy, and one way to do that, for example, here you can use ADC, analog to digital conversion. You do the sampling, you convert the analog signal into its digital form. Well, it's as simple as that, right? This is what we do when we talk about, sensing that you have some kind of signal. Well, it's in the form of energy. You just want to read it. So one simple way of doing it is just using ADC, and you can get the signals. Well, there are a lot of things that can be sensed. Let's expand our problems or the applications. And there's so many things out there. For example, gas, smoke, permittivity, radiation, stress, light, pressure, and so on. So when we talk about sensing problems, and if we want to limit this to NDE, there are a lot of things can be, captured using sensors. And this is a true multidisciplinary area. Well, we can do the data acquisition using ADC for each of them. So let's look at an example here. For example, two different applications, right? One is it's a tire. The second is a spaceship. So what is common in between a car tire and a spaceship? Both are pressurized, right? So how can I get the information from here that I can use sensor to measure the pressurized information? But of course, you have to deal with different conditions when you are doing this sensing or doing the pressure measurement for a car tire and a spaceship. You'll see so many applications for sensing acquisition out there in the sector of energy, agriculture, defense, transportation, and so on. In day 3 of this course, I think with the examples we had in the previous 2 lectures or 2 days, that hopefully we'll have a rough idea that what applications that we can apply our knowledge to after we learn these concepts in this course. And in day 4 and day 5, you'll see examples in agriculture, and you'll see examples in energy. Of course, we've talked about examples in defense and transportation. So new sensors acquisition methods are needed for different applications, and I believe I convinced you through the solution approach flowchart when we talk about the impacts of NDE and SHM. And new applications coming every day. Well, I mentioned the differences and the things in common for NDE and SHM, but if you look at in terms of the sensing acquisition, then you see both concepts or both techniques will apply or fall well into this domain. And you'll see similar story is with the ND and SHM community as well. Although you usually will divide them into two close related but different communities out there. In terms of applications, I would like to list three different materials that we're dealing with on a daily basis when we're doing ND and SHM. But before that, let's have a quick review on the common and differences for ND and SHM. I use an analogy at the time, let's say for similar to medical devices. NDE is how we can use those large capital and more expensive localized measurement techniques in hospital, for example, X-ray CT, MRI, PET, and so on, to give you the exactly nature of your disease or what's going on in your human body versus monitoring techniques, which are usually global, low cost. And if you look at the way you can collect the data on a much, much larger population, and sometimes you call that a distributed monitoring or sensing. And for example, you can have those handheld, you know, wristband type of devices to monitor your blood pressure, cholesterol level, heartbeat rate, and so on. Well, for industrial applications, for engineering applications, this is very similar. That for NDE, usually you mean a offline um, and more in-depth evaluation of what's going on in terms of the damage, in terms of the material state, in terms of the structural performance or the complex systems, status and so on. Well, for SHM, you have those global information measure, for example, the overall um, uh, vibrational characteristics from a structure like a bridge or like a tunnel, or you can apply a lot of sensors, distributed sensing mechanisms to a complex system, for example, an airplane, to a suspension bridge, and so on. So you can get the overall health condition of a complex system. But things in common, and I remember in 2012, I delivered a talk talking about overlap region or overlap applications for ND and SHM. Most of them are seeking to find the best sensing capabilities and approaches to gather data, and especially more importantly, as I point out, the information out of the data to tell you what's really going on there. And for NDE people, we also look into not only localized information, but also global information. We want to make our sensing cheaper, and sometimes we want our sensing to be in a large scale data acquisition approach. Now, SHM, of course, they want new sensors. They want to know more about what's going on there. So there's overlaps between ND and SHM. So you can see the subtle differences and also things in common. All right, I believe I set the stage well in a course like this. And I believe the topic we'll talk about today, guided waves, is a perfect technique that you'll see in both ND and SHM. If you look at what's out there, you'll see that guided waves is being used widely for ND problems. So is in the SHM community due to its advantages in covering a large-scale structure, and you can let the guided waves to propagate longer distance while still maintain the advantages of capturing what's going on there in terms of damage assessment. Well, for different materials I listed here, for example, metals, we can have iron, copper, aluminum, steel, and many more. This is a material that has been well understood over many, many years. Well, when we talk about new or emerging materials out there, plastics and composites, for example, polyethylene, polyamide, PVC, and you'll see this used a lot, particularly in energy transportation industry, for example, pipelines. And for composites, we've seen the motivation of using composites in aviation industry. Today, we'll talk about composites using automobile industry, and many more areas are using or adopting those lightweight materials. Just give you a very quick view, and I am sure you will appreciate that the numerous applications out of those different materials, as I just listed quite a few of them here. Well, for different materials, you can see that I'm interested in different problems. For example, for metals, I am interested in cracking, corrosion, fracture, and for example, the welding between metals and dissimilar metals, and how I can evaluate the failure there. Well, for plastics, there's bond failure problem where you fuse plastics together, and there was an interesting project we did for gas pipeline industry to evaluate the bonding quality of polyethylene. I don't know if I have time in this lecture to cover that. If I do, I'll be very happy to cover that in our following lectures. If not, I can direct you to some of the readings, although some publications has not been out yet. But this is an interesting problem. People are realizing that the failure of the plastic joint is not mainly due to the volumetric defects, which are easily to be detected, for example, using phase array, but you'll see those bonding failure of plastics. Some of them are very difficult to detect using sensing, but it's out there. We call it cold fusion problem. So you don't really have a defect there. The defect here in terms of volumetric defect or discontinuities in materials, but the materials are continuous, but just the bonding quality is not good at the molecular at the microscale level. Fracture of plastics, permeation in the plastics, for example, hydrocarbon permeation, when you have plastics to transport, for example, oils or gas. Well, composites, due to this complex nature, and there are so many ways of fabricating composites out there, and there's a lot of problem associated with it during its manufacturing stage and also its service stage. For example, bonding, voids, cracking, delamination, misalignments, fiber breakage, and so on. And you'll also see some applications here today. So the common physical parameters as a course like this, let's go back to the fundamentals. what you try to measure in physics out of those different applications, out of those different materials, that you can actually limit them to a few things. For example, I want to measure the conductivity, I want to measure the permittivity, permeability, Young's modulus, elastic modulus, dot, 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 through sensing. Well, we are now having a forward problem starting from the physical space. And then we're trying to get the sensing done and have the data acquired and moving that into a data space. And very soon, I will introduce a concept maybe some of you have heard. It's called CPS, cyber physical systems. That you have both physical systems and you have cyber system as well. Well, for the acquisition side, what we are trying to get, or we are trying to digitized or sampled, are the physical quantities or parameters. For example, resistance, capacitance. Those are impedance, inductance, right? And those are the physical quantities I want to get from acquisition, and I need to have different way of doing the sampling and digitization there. And you can see the subtle differences here when we talk about sensing and acquisition. That sensing, you are trying to get the physical quantities or the parameters more associated with the materials level, and well, for the acquisition, you are trying to get those physical quantities when we talk about measurement. So I list the common NDE techniques here after the first course offered by Professor Udpa and my previous day 1, day 2 lectures. We are exposed to numerous NDE techniques here. And all techniques are amazing. They were invented, they were developed, getting matured. And you see, most of them, if not all, works perfectly in lab environment. Well, when we move this into the field operation, sometimes issue will come. And there are still technical gaps. As I point out in today's lab session, that when I have some technologies, for example, the new EM sensors we developed for CFRP plus steel structures, and when we move that into the field, we'll deal with a lot of uncertainties when we have the field measurement. So keep that in mind. There's a lot of technical gaps out there for even those well understood in physics and amazing technologies for NDE problems. So if we want to combine NDE and SHM, we have to fill that gap, because NDE, traditionally, you can work that in lab environment, you can work that in a factory setting and maintenance site setting, that you can do this in a well-controlled environment. But for SHM, you are doing the same sensing, you are doing the same data acquisition, but you have to deal with the field condition. Just imagine those windmill farms or those large wind turbine blades out there, which is rotating 24/7. So rethink ND and SHM, rethink that the techniques we developed, we learned in this course, we want to apply in our research, and we want to apply this in our industrial problems that works from height of a wind turbine to buried underground pipelines. And everything should work in a well-controlled environment, as well as a field conditions with tons of uncertainties out there. So ideal ND and SHM should have those common traits or attributes here. For example, I want my measurement to be fast and accurate with no or low downtime for my system to do both evaluation and monitoring. And hopefully it can be self-diagnosis. Yesterday I talked about this is one arm or one branch to make the next generation in the NDSN possible. And for self-diagnosis, we are trying to make it smart in the sensing and data acquisition. So we can achieve, for example, the following scenarios: that no wind turbine start for maintenance check. Is that possible? No excavation for pipeline check, that you don't have to dig things out to do the in-ditch NDE, but you can let the pipe doing its job while still check the condition of a pipe. No hangar visit for basic routine check of airplane, so you can let the airplane perform its service. So you can have the in-flight monitoring and evaluation and self-diagnosis. Well, think about those scenarios. We have had some limited success out there. I have to admit that we are doing some great work out there. For example, for wind turbine, we can have the house monitoring when it's running. We can have inline inspection tools, or sometimes you heard this is called PIG, pipeline inspection gauge. When we have the pipe running, we send the inline inspection tool inside the pipe, moving by the pressurized gas and taking data, so you can do the assessment after retrieving the device with the data processing or inverse problem of NDE there. You can do a lot of in-flight monitoring, and think about the airplane. It was equipped with so many sensors on board. But there's still technical challenges out there. Think about the same three applications, that we are still not getting all the information we want from those practices. And sometimes it's really difficult to do that. For example, for pipeline problems, some pipes are not easy to be picked, as I give you a brief introduction in day one, due to the complexity of the pipe itself or small diameters of it. Well, for airplane, you still are relying on a very limited bandwidth and sometimes obsolete way of communications, where you're collecting data on board, but you don't have a very good way of communicating that data to ground locations for data processing and for real-time communications and decision making, right? That's why we're still relying on the black box, those signal storage, or those data storage devices on board. If there's some catastrophic failure, crash of an airplane, people are still heavily relying on the device that doing the data acquisition on board, instead of having some real-time communication with the airplane. So if we can develop an ideal NDE and SHM, merge them together, well, we'll make NDE cool again. That's a philosophy. And that's a philosophy we students, while taking these courses, while learning the forefront of this area, the cutting edge technologies that we are learning here, and it's not possible. It's not possible, and even not our intention as educators and researchers to give you everything within 5 or 10 days. But we want you to think in that direction. And what you learned here can be applied to different applications. And let's make this field cool again. And I don't know how many of you in the audience are actually doing NDE. And I really appreciate if some of you are not NDE field, you're still interested in taking this course. But I assure you, this is a very cool field. If not sound like a cool field now, but it will be a very cool field in the future. And I'm a strong believer of that, not only because I'm a professor in this area, but because if you think about the future, and if you think about the future engineering practices, and not mentioning the different cool applications I identified in this area, but instead of just like what we're facing in our society growth, we need to have more materials, new materials applied. We have to have new infrastructure applied, and monitoring, evaluation, testing, certification, and recertification of those new materials, new infrastructures need the next generation DE. Okay, so I will stop here, and we can take probably like a 15-second break and think about what we just discussed, and lead to a stage that I want to have both NDE and SHM, and I want to get advantage from both fields, understand the common differences, and apply this to our problems, research problems. And in this course, since this is the inverse problem, data processing course, and we'll choose one. In today's lecture, we're going to choose a couple of applications in the morning and afternoon session and try to understand the concepts what we just learned. And we chose guided waves, which is a perfect technique that we can use for both NDE and SHM. All right, so any questions before we move to the details of a guided wave NDE and SHM? All right, very good. So next, 1 hour and 30 minutes. So I will talk about how I can apply guided waves for the application here, which you'll see it's a new concept that we can use for manufacturing in automobile industry or automotive industry. And this can also be applied to other applications, but I think it can be easily figured out. But it's not maybe a good time to talk about this. For example, military applications, defense applications, and so on. But let's focus on automotive industry. Okay, I see there's a question from the chat. Let's take a look at that. So Shanka asked, what's the difference between plastic and composite materials? Okay, good question. Well, first of all, I have to admit, I'm not a material science expert, so I'll try my best to answer your question. So in terms of NDE people, the plastics and composites are different. Well, plastics, we will most of the time talking about those polymers. We'll talk about those materials not necessary to be a composite material. Well, composite from the name, usually it means that you are going to have multiple materials. You make that in a way that it can achieve some desired material properties. And that's why you call this composite, right? Well, plastic is not necessarily composite, although it's possible. And the traditional composite material definition is when you, for example, you have carbon fiber, reinforced polymer. You also have polymer there, right? It's in a polymer matrix, but you have carbon fibers in it, so which it should give you the strong, for example, yield strength in some directions, in the same direction of the carbon fibers there, and you put that in a polymer matrix. And in that case, you have more materials, right? Well, let me say a little bit few things more that you also gonna have the join of the materials. Then you can have the plastic materials join, you can have composite materials join, and you can have the same material join for plastics and composites, and you can have dissimilar materials join as well. So I hope I answer you the basic difference between plastic and composite, but there will be better answers out there if you go to the fundamentals of material sciences. Okay, but we usually treat them as different materials as NDE people. Hope I answer your question, Shankar. So any other questions? Very good. All right, so now let's look at this problem. So I will start with this automotive industry problem where I talk about reversible adhesive. And like life cycle of RBCS, we'll identify the challenges objectives here and introduce a guided waves based approach to do several things. One is a bound line process monitoring, in-service fatigue prognosis, and composite material characterization. We have some preliminary results. We actually have a PhD student just graduated early this year and joined a DOE national lab. And hopefully we'll identify some challenges out there. And since this is a course that I hope that we can have more fundamental research questions touched and discussed at the end of this module. Well, the motivation is clear. We have some motivation discussion for composite usage in aviation industries. For automotive industry, it's also very obvious and it's a strong motivation. We've seen this left figure before, for the Dreamliner 787 or 777. You see the usage of composites there. For automotive industry, this is a figure showing you how those composites have been used for different parts of a car. Well, the manufacturing aim here is we want to have the performance composites. For the aviation industry, that for aviation industry, we usually have no limit on time and money. The performance and safety is the highest priority. So usually it's complex, time-consuming, and expensive monitoring solution can be used for that area. But for automotive industries, we have time constraint, cost constraint, when the safety is also important. I'm not saying that for automotive that's not important, but comparing to aviation, that's a different story. So we're looking for reliable mass production for the automotive industry manufacturing when we're dealing with composites. And mostly we'll deal with multi-material joining. We're joining composites to metals. And we want to have robust and quick and reliable monitoring in a manufacturing setting for automotive industry. And we have to keep these different aims in mind when we talk about different applications. And as an engineer, that I want you to understand different, aims lead to different ways of doing the design and practice for NDE and SHM. And also you'll see that this is a very slow transition. I'll call it slow because you'll see the resistance and the hesitation coming from industry. When we have new materials coming in, then we'll have new evaluation, new monitoring techniques out there. Well, people in industry are slow adapter to the new technologies, which I think is good. I don't think it's a bad thing. Let me give you an example, and sometimes it sounds like a joke, but that's a reality. That we visit a factory who make automotive parts, right? And before we use a lot of composites in automotive industry, people use metals, and for metals, there are different ways of using metallic materials. You can also have lightweight metals there. You can have conventional metals there. But how you join metals together? Are there different ways of doing it, right? Some metals you can using welding. Some metals you have to rely on mechanical, fastening. That you can have rivets join different metals together. So when new materials coming into coming into play, then people try to use composites. But how to join composites together? So we actually visit the factory and we will share the story that at the very beginning, field workers try to join composites together by drilling holes and put rivets to it. And then they use rivets to join composites. Well, that sounds like a joke, right? So you have the lightweight composites, you want to join them, but the field workers say, hey, that's the best way they can think of. If they don't have another new way of certifying joint composites, if you want to use glue, well, everything can change. If you want to glue things together, because you cannot easily weld composites together, right? So the best way is just use rivets to fasten them. But is that the best way to do? It sounds like a joke that you drill holes in composites and join them, but you still see that, right, out there. Another thing that we realize in the field, for example, if we want to make a component out of metal and out of, let's say, carbon fiber reinforced polymer, CFRP composites, should I weigh them and make them into the same dimension I made before? I have a part designed with these dimensions. When I want to replace the material, what's the size I should make? Should I make them into the same size? Or should I make it smaller? Smaller sometimes means can I make it thinner in one dimension so I can save the materials and of course save the weight further? Can I do it? People have to answer that question, right? And this question, I believe, has been asked many, many times and trying to answer many, many times when we try to do this in the manufacturing. And you can see the transition here, and you can also see the associated challenges out there. Keep that in mind when we actually at this, at this stage. Well, the transition from bolted to adhesive bonding, and I had that story and try to give you some time to think about, you know, about this transition, that I can use mechanical fastening to join two materials together. Well, for composites, what does it mean? I can drill a hole and put or join two composite layers together. But if I drill a hole to a CFRP, that I am introducing new damages there. I'm drilling a hole there, I'm break the fiber, and that will introduce new integrity deficiencies there. Okay, I don't want to do it. Is there a better way of doing it? I can use adhesives. And hopefully the adhesion is good in quality that I can join those two materials together. Well, the advantage of doing adhesive bonding is, you can make this lightweight, it's cost effective in fabrication, no stress concentration and delamination when you have those mechanical fastening there. And if you tie those rivets or fasteners, tie more and more, that you are introducing more stress concentration. Well, adhesive bonding, you don't have that problem. But what's the disadvantages? Well, we have new way of doing manufacturing here. Well, unable to repair damaged bond line or substrate when you have something going on there, and unable to disassemble and reuse after the vehicle end of life using the conventional adhesive bonding. And of course, it's also bring challenges in evaluating the bonding quality when you have new way of doing material drawing for composites. So let's talk about a new concept here called reversible adhesive. So I can have different ways of doing adhesive bonding, and in terms of the materials there, or in terms of the way they can, um, you know, uh, be understood in two terms. One is called thermoplastic, the other is called thermoset materials. They're going to have different behaviors subject to heating. So for adhesives, you can have thermoset. And thermoset materials, they cannot be reversed. It's a permanent bond after you cool down. Well, for thermoplastic, those kind of adhesives can be reversed by applying heat again. So when it's cooled down and when it's reheating, then you can have this adhesive reversed. Well, we're gonna apply something in lab condition. We can use oven heating and also induction heating to introduce this or demonstrate this reversible adhesive concepts. Well, we'll see a new way of doing induction heating, and since this is the electromagnetic, well, although we talk about guided wave today, but we are using electromagnetic induction to heat the adhesives and introduce the irreversible adhesive concepts. And for induction heating, usually it's a targeted heating, not only because that you can have those heating in a local fashion, that you can, for example, you have this inductive coils, you can have the heating just within this coil because that's where most of the field and energy being concentrated. There's also can be in target heating if you introduce or improve the adhesive properties by introducing, for example, conducting or ferrite, ferromagnetic material nanoparticles into the adhesive materials. In that way, then we can make that material or adhesive layer selectively absorb more EM energy, so you can have more temperature rising, so to achieve targeted heating. So this is something I just mentioned. You can combine thermoplastic and ferrous nanoparticles, so you can have a selectively heating region. Let me just show you a video. This is a video captured at in our lab. That those are two. This induction coil there. Selected way there is two composite plates. They just detached. Let me play this again. Right, reversible adhesive to disbond those composite structures. And we call this RBCS reversible adhesives. And we will have more advantages here to make it easy repair and healing of bond line damages. Think about those thermoplastic nature that you can bond it, cure, have good bonding strength there, but you can also repair it by disbond it. You can have some self-healing, a characteristic for those bond line damages, which I'm going to show very soon. And you have rapid processing and dismantling and reusability of composites. I'm sorry, reusability of components at the vehicle end of life by adopting RBCS. Well, the disadvantage is only non-conductive substrate shall be used if you are using this electromagnetic target heating, because if it is conductive substrate, then your substrate will also be heated, right? But there are more research can be done that can I do a better job in target heating. So the EM energy will be absorbed more in the adhesive layer. So when we talk about life cycle of RBCS, this composite structure, there are 4 major steps. For example, in the process of reassembly, how I can have this processing, bond line quality monitored using our technology developed here. In service, when it has in-service loads, how I can evaluate. In repair, can I do healing and self-healing and effective repair of those RBCS structure? And in disassembly, can I achieve an easy and safe disassembly? And then you can go back to reassembly again. So this is a very good way of understanding the life cycle of RBCS, and you can see the use and reuse of the materials. And at each stage of this life cycle of RBCS, there are technical challenges dealing with the bond line quality monitoring and in-service loading when it is in service, and repair, disassemble, then reassemble again. In today's class, I'll try to focus on some of them, not all of them. So we'll talk about the advances in the monitoring and also in service loading, monitoring, and evaluation. Okay. Stage 1, challenges in processing bond line. The challenges, unlike oven, we can have induction heating here. Well, induction is rapid in nature. That makes it harder to achieve isothermal bonding. And complex heating mechanisms make it harder to predict the temperature of adhesive. So this shows you for the ABS polymer here, when we try to increase the temperature and same time measure the elastic modulus, we heat it from 20 degrees room temperature up to 160 degrees. And you have this transition region where you have the elastic modulus significantly dropped when it's over 100 degrees C, and it's melted and the elastic modulus dropped to 0, where you have this glass transition region at around 110 degrees C. And after 160, you have permanent damage to this ABS polymer. The common defects here when we try to do this heating is you're going to have chemical degradation of adhesives, and sometimes you're going to introduce kissing bonds there. So I want to have a real-time temperature adhesive state monitoring. If we can do that, we can have a well-controlled process. And you want to have a control to control the induction heating system to obtain optimal bonding. And you want to have this working in some optimal heating zone. But how can I do it when I'm doing this in a bond line stage? So this is a process monitoring problem. The objective, which is listed here, the same objectives here. So one way of doing it is you can use a fiber optic sensor. This is an expensive but very high accuracy and precision system called Luna system, where you have fiber optic to measure inside adhesive for its temperature changes over time. Well, the temperature of adhesive can be measured instantly and more accurately. But the problem is the fibers act like a flaw when you have those fiber embedded in adhesive. Um, they are just foreign materials, right? And also, they are fragile and expensive. And each sensor here will cost about $500, right? And this is not very economic to do it. But we start from this solution and give us real-time, instantaneous, and accurate monitoring of the temperature there. Is there a better way to do it? The answer is yes. We can use guided wave sensors. You've seen these guided wave sensors in previous fatigue loading or fatigue cycle loading test, where we try to evaluate the composite materials, where we introduce different kind of fatigues there. And for bonding, we also developed a technique where you can use this GW method to measure what's really going on in the adhesive bonding quality. So we don't have to introduce a foreign material like a fiber into it. So it carries the information of waveguide with them and can travel long distance, and there are mechanical stress waves. And think about the mechanical stress waves propagating one substrate to the other in between the adhesives. And the energy will be transmitted or be sent from one transmitter to the other PZT receiver more when you have a better bonding quality. So we start from simulation study, so we can have those dispersion curves, the frequency versus wave number, and you can use that to identify the best mode when we have this particular geometry and adhesive between. So you can see that for different modes that you can have, for example, You can find what are the most sensitive modes sensitive to the adhesive condition there. And you can also choose the right frequency when we're dealing with those structure. So from the dispersion curves, for in this case, we're going to have the phase velocity, group velocity versus frequency, and you want to look at one mode that can easily be used for our monitoring, and you identify, in this case, for this particular frequency, that you can see the difference here in group velocity and phase velocity, and you choose that particular frequency around 3 or 3.5, I'm sorry, 35 kilohertz in our excitation zone here as our exciting frequency. Well, you also see different mode conversions, as you can see from here when you have this spectral structure. Well, we start from FEM study. So finite element analysis tells us how those energy, guided waves energy, mechanical waves can propagate from one to the other. And one way of generating the selected L0 mode, we have a very good way of doing that is a co-located PZT wafer that you have those two sensors apply there, so you can generate a good L0 mode into the substrate. And we simulate the PZT transducer at the end, where the PZT transducers with applied electric potential and generate the mechanical stress waves and propagate in the material. And this shows you the FEA results, where you can clearly see for different temperature, you have fully cooled sample as source energy will be transmitted from one. Easy to see for fully cooled, you have bottom, and you also have a displacement snapshot at one time instance, time 90 microsecond, versus partially melted. So the FEA clearly show that at different temperature, how the adhesive will behave. So from that, we can calculate the transmission coefficient. These are the simulation study. So you can get the signal amplitude versus the time. Well, this is the simulated PZT response. Remember, you have two PZT applied on each substrate end, and we can measure that. So you can see for fully melted, then this amplitude is 0, right? So no energy has been transmitted. Well, for half melted versus fully cured, then you can clearly see for the fully cured, you'll see the energy or the signal has been captured. Well, you need for rapid signal processing guided with parameter identification, so you can have a better understanding of the adhesive quality at different temperature. So there will be signal processing technique out there, and you can extract the parameters for guided waves and then do further data processing and classification. So this is similar to what we did before, what we learned before in signal conditioning, pre-processing, feature extraction, and classification of different conditions there. So one way of doing it is you can look at, for example, the signal, then you look at the ES, which is taking the Fourier transform of the S squared, well, S is nothing but the Fourier transform, as you can see from here. And you can calculate the transmission coefficient definition we will define here. You take the Fourier transform of the signal in the time domain, then you take this is more like a squared S, the frequency squared component, and integrate that over the F1 to F2, the frequency range. Then you can get the transmission coefficient as a ratio of ESN to ES0. And you can see the transmission coefficient versus temperature, that you can have a good transmission of energy for low temperature. When it's going to high temperature, it's melting, then you have less and less transmission from one to the other. Well, recall what we actually seen before. Let me show you. This is what we measured, the elastic modulus, and it's very similar to what we're getting here from the guided wave measurement, right? So this demonstrates that we can use this transmission coefficient to understand at different temperature what's going on in the haze sieve layer. And everything here is simulation study. We want to validate this in experiments. Right? This just tells you the correspondence here for 30 degrees, 110 degrees, and 130 degrees. So how we can make this real-time bound monitoring with a feedback induction control? The reason for that is we want to control the temperature. So this is a design that you have a guided wave system which can measure the energy from one to the other, from top substrate to bottom with adhesive in between, while at the same time we apply fiber optic sensors so you can have an accurate temperature measurement at the same time. Well, the PC plus data acquisition algorithms give you the real-time monitoring capabilities. Everything's being written here in MATLAB. Of course, it can be optimized. Right, so you have those optical fiber measurement system, you have the guided wave systems, and from this control unit, you can control the EM induction heating to make it optimized for the temperature heating and have a better understanding and control of the adhesion condition here. Right, if we look at this particular region parts in detail, that you have this PC to control the function generator to send the guided waves, and you will have this targeted heating where you have ferrous nanoparticles in it. So you can selectively heating this yellow region, and you can measure what you're getting at the receiver PZT. At the same time, this will give you the information in real time, control the induction heating unit, so you can control the quality of adhesion here. Well, this tells you the experimental results. Well, comparing to the transmission coefficient you are getting in the simulation, well, we can do the same approaches in calculation this transmission coefficient. But one thing you noticed in the experiments that you'll have electron noise interfering with the DAC system, and even for fully melted, you still have some energy transmitted through, right? So this is something that you have to deal with in the experiments. Well, in simulation, it's you know, it's going to be exactly zero. Well, if you look at the transmission coefficient, and this is a very interesting result, that you are going to control the temperature over time because of the feedback loop there. You control the temperature, so you can see the transmission coefficient dropped significantly when you go to high temperature over time, then it's going back. This is the cooling stage. That you can have this nature. What does this mean? It means that you can have this work as a reversible adhesive, right? So you're gonna melt, you're gonna have less energy transmitted, they're gonna detach, dismantle, then you're gonna bond this again if you cool this down. So look at the optical results. You compare that, you know, with guided wave control system and without guided wave control system. Remember that you're going to measure the guided wave signals, then you can use that to control your heating or induction heating into the adhesive region. Without the control, you'll see the temperatures will go up, skyrocketing very quickly. But with guided wave control system, you can have a better way of controlling the temperature in this adhesive region. And you can have PWM strategy, pulse width modulation there, strategy, and to better control the temperature or temperature rise over time. So by doing this, you're having the information coming from your guided wave measurement, and you can use that information to better control the process. And the process here, of course, it's highly correlated with the temperature changes. So you can use that to control the bonding quality. And at point B, you can look at the temperature rise over distance, and you can see it's not constant over the distance there. Well, you can also see at point C, when you rise this at this time, then you can also see the temperature in the sample versus the distance there. Here, the distance along this direction. And at D, you can also see the non-constant distribution there. So the optical fiber will give you more details. And you also see that the temperature is not the same everywhere. And this brings more challenges and tells you that the temperature is not the same everywhere along the distance or along the direction of the guided wave is propagating. And this gives us more information and more challenges and more ways how we can better control the temperature in the adhesive layer. So you can compare the OFDR and GW results, and you can have the temperature measure from the optical fiber, and you can also have the guided wave. You have both FEA transmission information. You fuse that with experimental transmission data, and you can use that to get the elastic modulus calculated and do the comparison here. You can see for optical and guided wave, well, it correlates well. And it tells us that guided wave technology is successful in identifying the adhesive state while doing this bond line processing. Right? You can achieve the same thing now. You don't have to embed any sensor in between. You still can have this non-destructive way to measure the temperature and eventually infer the elastic modulus there. And you are able to control the induction process by designing this new controlled target heating method. There are new ideas that we can apply, and I will just show this to the class. This is an open-ended research question. We are working on that. We don't have fully complete this, and this actually in our research proposal being funded recently.
Yiming?
Yes.
Yeah, any issue of recording? Mean to say for this?
Yeah, it's okay. You can record this. That's fine.
Okay.
Yeah. So this is some idea that we propose, but it's okay that we share with everybody. Um, so we can have a long bound line monitoring using EM sensor. So for example, you can have a pancake style induction coil. Instead of have a small structure putting inside the induction coil. Now, how about we have a pancake compact induction coil or even a coil array design that's moving along the join direction. So over a longer bond line, you can have a new way of heating and cooling using this pancake style induction. And every time, only a small section will be processed at a time, then the bond line will be processed gradually from bottom to top, as you can see from this picture. While at the same time, for this long bond line or large structure, you're going to have a sensor network. So you have multiple transmitters and receivers on both substrates. Well, this brings more challenges in the data processing as we are getting more data. And this is a typical inverse problem setting here, that I have multiple sensors working in multi-transmitter, multi-receiver mode. Well, you see this inverse problem in audible signals or acoustic prob setting a lot, right? And a famous problem is called a cocktail party problem, right? That in a cocktail party, then you have different people talking, and you want to identify the sound sources or the location of the people who's talking. Similar here, you have multiple transmitters and you have multiple receivers, and how you can assess the bound line quality while you are hitting using a new sensor. So new challenges there, MTMR sensor deployment plan. You can have new processing of the signals, new control technique there, how to design the mobile flat induction coil, and you can always start with a new simulation analysis, right? So those are the concept that is going on, and although we don't have a solution there, but I'll be very happy to share with you, and you can also think about that. All right, so we can move to the next stage. We talk about the the process control or monitoring, where we actually make the bound line there. Then in the service condition, where we have fatigue loading there, where we have the structure in service subject to fatigue loading. In the automotive industry, we can actually make this more understandable, that we have a car, we have those composites being joined using these reversible adhesives. Then this is running on a bumpy roads for a longer time, or this vehicle is actually in a military service or in a battlefield, subject to some impacts due to bullets or hopefully not missiles, and is subject to some kind of loadings, and how we can evaluate the quality of it. Well, we studied this at a fundamental level in lab, and introducing cyclic loading there. So you have the substrate joined by the adhesive. This is the same lab joint structure, and we apply cyclic loading, to mimic the realistic fatigue problems in the field. Well, a couple of challenges being identified here, that only fatigue load and associated bound line are the weakest link damage is considered here. Although we have a lot of more complicated realistic conditions or damages out there, but we have to start walking before we can actually run. And fatigue is a very important problem to be noticed. And they do not show sudden property changes, and it may fail at a fraction of a static strength. And it will develop very quickly at the end of the stage. And we want to understand this fatigue, but still it's a very challenging problem to tackle. And loading and associated damage being complex it make it very difficult to predict the remaining useful life. Okay, so based on the lectures yesterday, okay, I hope the students are prepared or at least understand some concept of prognosis. So we'll see this further in today's lecture and how we can, using prognosis for this particular in-service RBCS structure study. So in cycle loading, in this particular problem, you'll see under the loading, the cracks will initiate from both ends of the adhesive region, and it will grow over time. So when these two cracks or the animation will reach to a point, sometimes not necessary to be connected, then under the loading, you'll just fracture rapidly, and you have a large delamination or fracture site there. So objective here is, can we have a real-time fatigue crack tracking and prediction or prognosis here with RUL estimation? So yesterday we look at a problem where we try to estimate remaining useful life in composites, where we use guided wave and optical transmission technique. At the same time, at the time, it's different problem setting. It's a mode 1 fatigue, where we have oh, no, I'm sorry, that's not a mode 1 fatigue. That's a tensile test where we have a GFRB coupon with a drilling hole in between. But now we're studying the adhesive bonding quality subject to the fatigue loading. Well, you'll see some of the same slides here. I just want to show this to you. Just have a recall of what we covered yesterday, right? Okay, and I don't have to explain this again. The same concepts here, that you use multi-model NDE and prognosis to understand the damage state, or here the damage level over time. Okay, so for the this particular problem, when we talk about the damage mechanisms and damage growth model, we start from the presting state. Subject to cyclic loading, then you can have a crack initiation. We always want to understand that, so we start from the optical technique. You can actually monitor or assess the fatigue crack propagation, and you start seeing the location of the crack initiation from the edge of this adhesive layer, then it start growing over time. And you can also measure that optically, how that grow over time in space. Then it grows from both ends, then at some time it will lead to failure. So what we introduce here is called an effective area, where you have effective area to couple the energy from one substrate to the other substrate. And the larger this effective area is, and the more energy will be coupled. And this can be correlated with our guided wave signal parameters. So from a top view, you can convert this into a 2D effective area. So if my measurement can be found to be correlated with this effective area, then I can have a way to describe the damage and its growth of a damage using my NDE technique. Well, we adopt the same damage model. Remember the Paris model we had before? In this case, that you'll see it also follow a similar pattern. And for adhesion region here, it will grow at a different rate for region number 1 and region number 2. Or here, we call this crack initiation. Before that, you'll have a different damage area change rate. Then you'll have a second region followed for the crack growth range. So same concept, so I don't have to explain this again. So we select this example so we can visit this problem again. But the key takeaway here is we have this new model, we have the parameters to be estimated. Here is the M1, C1, M2, C2, and P star or N star is the transition or jump time here. I hope you still remember the M1, C1, M2, C2, where we use this Paris model, where C is a coefficient, M is a power. So basically, we are using the C delta K to the power M model here. So we can study the change over effective area or damage over time or over cycles. Okay, so we set this up in the lab. You can see this in a more closer look. The MTS data acquisition system and the guided wave data acquisition systems being set up, everything is being done in real time and in situ, so you can monitor everything at the same time. So the also we have the laser extensometer there that the specimen is in between. So the MTS can output the force applied there, the shear strain, while the guided wave will output the energy transfer from one substrate to the other substrate. It will also perform the model analysis there. And based on the guided wave signals, you can calculate TOF and doing the signal processing. Okay, so the effective area can be calculated and found to be proportional to the force applied over the shear strain and the shear modulus. And in our MTS machine, you can calculate the effective area versus the fatigue cycle. Remember that those terms can be calculated or measured using our FMTS data acquisition system. So this can serve as ground truth in our analysis. And we convert this into effective area versus fatigue cycle. And you can clearly see these two regions, right? Those two regions where you have different parameters if you're using a damage growth model and you have a defect or damage initiation and also the following by the damage growth region. Well, for this guided wave method, we have to select the best frequency based on the dispersion curve. So it's important to analyze the dispersion property of the substrate. You have different ones. You have to do that every time. So you can excite a single mode at this particular frequency. So you can differentiate that, right? You can differentiate that from different modes. You don't want to work in this region that you can have, confounding effects that you won't be able to differentiate it. So you select this mode at this particular frequency. For example, this is 20 kilohertz. So it can reduce the signal processing complexity. You have the same way, this is called lateral PZT excitation to excite the L0 mode and let it transmit from one to the other. Well, you'll get this measured at different cycles. And you can see at different cycle of fatigue loading that the voltage acquired at the receiver pair, which also associated with the energy being transmitted from one substrate to the other, is changing over cycles. And this definitely makes sense, right? That when you have 0 cycle and comparing to 550 cycles here, 0 is a resting stage, 550 you have some defects there. So definitely you're going to have a reduced voltage measured at the receiver PCT sensor. Okay, you did a similar transmission coefficient study, and you calculate transmission coefficient here. This is different from what we did in the previous application. We call this the transmission coefficient, ES here. It's proportional to what we had before for alpha, but anyway, if just ES versus fatigue cycle, you can see the transmitted energy over fatigue cycles. And F1, F2 are the lower and upper frequencies selected for analysis. In this case, since we chose 20 kilohertz, so we chose 15 to 25 kilohertz in this case. So you can calculate that transmission coefficient within that frequency range. Right? So hopefully I explained this to you in signal processing, why I chose those upper and lower limit, only because for different problems, you're going to choose your excitation zone for this particular from this particular dispersion curve there. In the previous example, a different problem, we chose 10 to 60 kilohertz, right? So I hope you can recall that. Okay, you also identify this jump time, or not necessary if it's in fatigue cycles, then this is N star instead of T star. I don't have to go over the physics or the methods of prognosis. The lecture notes are designed for this course. So if you take D2, if you understand that, everything here becomes easier. So I just show you the results here that you can do the prognosis. And from this guided wave measurement, you can actually capture these two regions, and with the initiation and propagation, or initiation and growth region, with the two defect area from MTS measured. Well, for guided wave, you can get that capture this defect effective area grows over time, and the remaining useful life can definitely be estimated. And I don't know if you noticed that or not. Our estimation or estimated remaining useful life is always an underestimation. Well, it is important, right? You will not prefer to have an overestimated remaining useful life, because that means a very aggressive strategy. In that way, that you'll have a consequence for the overestimation, which means you are too optimized, too aggressive. Then the actual structure or components will fail before you estimate it remaining useful life. So it's always good to be underestimated, but you can clearly see the error where you have less of available measurements versus more and more measurements. So the end of life for the specimen is assumed to be at a nice measurement at 550 cycles, and the predict useful life, remaining useful life, is close to the remaining useful life. Although it does not exactly match for most of the cases here, but it demonstrates the capability of obtaining the RUL from the developed model and guided wave measurements here. So currently, the state transition is manually fed to the prognosis algorithm for this particular problem, because it's not easy to obtain. So this is one limitation to it. The measurement interval needs to be smaller, and experimental errors need to be eliminated, right? So this is ongoing work. And the model analysis helps identify ideal excitation conditions at different stages of fatigue damage, and exploring the behavior of guided wave modes at this stage. As this stage will help us to identify stage transition from guided wave data. So there are some ideas that you can use by combining the model analysis, FE analysis, with our prognosis algorithms, which can help us to better understand the damage growth monitored by guided wave excitation. So the next two parts, I will just mention that, as I said, due to time, we won't go to the details of it, but these are other two stages for the life cycle of RBCS. Well, there are some ideas here which I definitely want to present and teach here in the course. For example, the repair or healing of adhesive is similar to bond line processing. In the bond line processing, you can change the temperature, so you can see the change of energy transmission from guided wave measurement, or from the two adhesive property, you can measure the elastic modulus change over time or over temperature. So let's look at the idea here. You've seen the red curve before, where you start from pressing, you heat it, the energy transmission will drop significantly, which means it's melted. Then it will going back to its healthiest joint state, where you reduce the temperature. Well, think about the new idea here, that I have some damaged joint. Well, the damaged joint is not because of the temperature or the changes or the heating, but it might because there are some defects in this adhesive material due to, for example, impacts, due to in-service fatigue. So this is our measure data. And for this particular damaged joint, you have this normalized energy transmission coefficient start from 0.4, which means there's some defect in it, right? But can we make this into a self-healed structure? So the self-healed RBCS can be achieved by controlling the temperature in the adhesive region. Well, this is a very cool idea that, well, you have a vehicle, it's bounded by those reversible adhesive mechanism. You have those reversive adhesive bonded composite structure in the vehicle. Now the vehicle subject to some in-surface loadings, subject to some impacts, and you can evaluate the damage. You first have to do this evaluation, right? You have to do NDE. You know where you are, and you can make it self-healing by target that region, change the temperature, reach to some point, then let it cool down. And we experimentally show that it can reach to its healthy joint because that's thermoplastic material, and we can heal the damage without the replacement, right? So this is actually a good way of doing repairing, or we use this adhesive healing to do the repairing of the structure. So this assembly may not require complex monitoring solutions. So studies now focus on the assembly most of the time. But we just show you this video before. This is a rapid assembly problem. Okay. So I have a couple of slides that I want to show you very quickly, but I will not spend too much time on explaining this in the lecture. But just want to expose this to you so you can understand how we can do, for example, materialization for composite adherence, for example, for fabric layup on mold, resin infusion, autoclave curing, and so on. The challenges are it require skilled labor to do that, and a lot of uncertainties on final product quality. And you'll see a lot of common defects there. For example, missing ply, wrong ply orientation, porosity, residual stress, improper cure, contamination, and so on. So one idea is if we can have a smart skin to achieve robust, rapid, and quick material characterization, how can we do it? So this is some pending method here. We have at MSU called Smart Skin that you don't need to permanently bond the sensors on the components, but it's more like a skin that can move that skin, or just like a carpet, move around the structure, and you can take the measurement. And the sensor can be reused multiple times and offer flexibility of deploying sensors in any array configuration. And because the skin type of flexible structure here, it can be attached to most curved and non-curved structure surfaces. And the transducers are fixed. So the distance are the same. Then you have a very easy velocity calculation. Well, this lead to a much simpler signal processing technique when we're dealing with this skin or smart skin type of sensing array. So the idea is you can make this flexible in a way that you take all those sensing simultaneously from the sensor network, while you still have some fixed distances there to make your signal processing easier. Okay, so I will just show this very quickly and how we can do this. We've done this in the lab, and we can use that to estimate the material properties. For example, modulus calculation, the Poisson ratio, density, plate geometry, using sophisticated signal processing. So this is an application not only for the damage diagnosis and prognosis like what we did for the previous 2 days, not for the monitoring of the bonding quality, but this can be used for material property estimation or material characterization as well, using sensor array enabled smart skin. Okay, this just shows you some results of estimated Young's modulus for this aluminum 6061 T6 material, and for different angles, you can actually estimate the Young's modulus very well using this smart skin. Machine learning can also be applied here, so you can improve that and using numerical simulation to generate a lot of data, and you can also using the smart skin to capture the real data, and using GW Kaileways plus machine learning technique, you can have a rapid material characterization. Of course, you have to train the model well and use that to to get the material categorization done, assisted by the AI. So one paper, you can refer this to our publication 2020 with one of my graduate students, that you can use ultrasonic guided waves based identification for elastic properties based on the 1D CNN architecture. So this is an interesting paper. If you're interested, you can read it. Okay. So last 15 minutes, there's some special topic of interest, and I want to show this to you instead of as a lecturing when we go to the details. Then I just want to show you some ideas, hopefully to make you motivated and excited and think about future research directions. For example, embedded sensing, how we can embed sensors into the composites. When we're doing composites fabrication, you can embed it the thermal signature in each layer. So you stitch thin wires or carbon fibers. Those are conductive wires, as you can see from this illustrative figures here. So you just stitch them in different patterns into composites. And this is the patent by one of our collaborators and colleagues here at Michigan State. And so each layer gonna have its own thermal signature, right? So this brings you a unique signature based on the unique wire pattern orientation at each layer. And you can heat those conductive wires by gel heating technique and capture that thermal signature using a thermal camera. What does this offer you? Then this process thermal signature could reveal various in-surface damages, for example, impact damage, delamination, and so on. And because it's unique to different plies or different depths, different thickness, then you can get this 3D imaging easily, because it's much, much easier to do the signal processing with these embedded sensors, right? There are different ways of doing embedded sensing. You can have the embedded sensor there to measure the physical quantities you want to get. You can also introduce those unique patterns using those embedded sensors, so you can get a better way to do the signal processing. This is a perfect example I want to teach in our inverse problem and signal processing class. There are different ways of doing inverse problems. You can get whatever data you get. You say, okay, my mindset is get as much data I can. I can improve the way I'm doing my sensing by having new sensors. Then I develop a better way of doing the inversion of signal processing. Well, let's change our mindset a little bit. In order to do a better inverse problem, in order to do a better signal processing, can we make our life easier at the beginning? Think about that. And this is a perfect example that we can have embedded thermal signature in the components that will make our data analysis simpler at the end. Hope that makes sense. You can also have, for example, embedded active structural fiber idea being better explained here. So you have, I list a few pictures here, some of them from internet. So you can have embedded sensors. Most of them are in patch design, like they act like a foreign body within the composites. But the embedded active structure fiber is not going to be like a foreign body. So it's not going to compromise the integrity or the strength of the composites. It's a first attempt to have the fiber-like piezoelectric design. Then you just weave or fabricate that when you're doing the composite manufacturing. Okay, so there are some papers out there. So I listed here, so you can read it when you have time. So these are some interesting ideas out there a couple of years ago. All right, so I would like to conclude my morning session here that the lifecycle monitoring RBCS is one of a kind. And by implementing the lifecycle monitoring, the overall reliability of structure will be improved. And the lifecycle cost is reduced, such as the quality control can be done, and we demonstrate that through the monitoring for processing defects. We're going to get timely warning on components health during in-service period to avoid failure. We also briefly talk about the repairs and the prediction through prognosis techniques help us determine the end of life or plan schedule maintenance or repair. This work is focused on reversible bonding components only, but the tool developed here can be easily extended to other structural components. That's why I would like to select this as a teaching example for this NDE inverse problem signal processing course. And also the reason to choose guided wave, as I mentioned, is it's a perfect technique that you've seen in both NDE and also structural health monitoring. For the future recommendation, or maybe I will not call this recommendation, but some future thoughts or research directions you can think of as the students of this course. And I hope you can have more ideas resonating, more thoughts came out from this, and you're very welcome to talk to me or interact with the researchers in this field. Well, these slides, I will just leave it to you. Those are well self-explained slides here. When I distributed slides with you, you can have that. So I will just skip this quickly. I know it's not my intention to go over this this morning. And I think I'm a few minutes before the class ends, right? So in the afternoon, we'll continue the discussion using guided waves, but we'll shift the gear a little bit. That in the morning we use guided wave to do, of course, monitoring. We use guided wave to do NDE and signal processing. In the afternoon, we'll see we use the same technology, but for different application. But still, this is the composites. So we have a concentrated topic each day. But we will see how we can do use this method to do imaging, inverse problems. And here I'm going to talk about a baseline free time reversal imaging. The baseline free means that you don't really need to have baseline information. So this gives you a lot more flexibility when you do the data inversion to form the images using time reversal technique. So this is just like quick preview for your afternoon. And with that, I think we're gonna have a few minutes for discussion and Q&A before we adjourn for lunch. All right. So I'll stop here. Any questions from the audience in the classroom as well as from internet? So let me go to the slides. I want to stop here. Yeah, very good.
Let me check online. Any questions from the online participants?
Okay, if no questions, which means probably I'm doing a great job here. You guys are getting all the course materials well. Well, I think always positively like that. All right, so if no more questions, I think we can adjourn here before lunch, and we'll see each other in 2 hours.
Yeah. So we'll wind up this session here and we'll meet again at 2:30.
Yes. See you at 2:30 then.
Yeah.
Yeah.
Thank you.
Bye-bye. Yeah, bye-bye.